So thank you for the kind introduction, and I really thank the committee for inviting me and getting me here. Enjoying my trip to India. And I've had a chance to interact with some of the students, and I'm really looking forward to more opportunities to interact with you in the next couple days. So today, I'm going to talk about AI/ML in applied weather forecasting, and the first part of the lecture is going to be, how is it used for decision support? In the second lecture, we'll get more into the foundation type models, but I'm starting from pretty far back on the history of AI. So how far back did some of the other speakers go on history? I bet you I go further. I know we heard a couple days ago about some of the foundations for AI. I'm going to talk about early artificial intelligence, starting with Alan Turing, who designed the Turing test. And you've all surely heard of this, where the idea is if you're asking questions to a system, and the idea is to tell whether or not this is coming from the answer is coming from a human or a machine. And for many years, nothing could pass the Turing test. But with the explosion lately, we're starting to see the Turing test be tested. About the same time, 1950, Claude Shannon built computer chess, and this is some of the first computers that are happening. But then when it started really taking off is when John McCarthy convened a conference at Cornell in 1956. It was that's where the name artificial intelligence was first coined, and it led to a lot of interest, and especially by the US Defense Department, and they wanted to see language translation, and a lot of the other types of problems were very heuristic, really built by human knowledge at that point. And then there was a period of time where there was a lot of work being done. We had, this one shows some of these first things. The ENIAC computer, we heard about that the other day, 1946. That's what got all of this going, Alan Turing. And we had a first AI boom. However, some of the results weren't what the sponsors were hoping for, and they realized AI wasn't making the type of advances they hoped for. So there was, here in the 1980s and 90s, or right in between the 60s and the 80s, an AI winter for a while, where nobody wanted to fund AI. Then came the second boom, and that's where we had expert systems show up that could make the type of decisions that humans did. Basically a lot of if, then statements, and logic composed into computers. But it too kind of got to a place where it wasn't advancing very well, and there was a second AI winter. Okay, and that's when I started working in genetic algorithms around that time. But at that point, we weren't calling it artificial intelligence. It wasn't popular, and especially when we were writing proposals to funding agencies, we ended up calling it things like statistical learning, just something that was okay to use. Okay, and then in the 2010s, that's when we had things like Watson won Jeopardy, AI beat a shogi master, and then the Go, coming up with new solutions to Go. And there's two ways of looking at it here. And what is AI doing? There were a lot of different types of AI that came up in the booms, but then these inevitable winters. But then we had, okay, come on. That's when deep learning beat the Go master. And, AlphaGo came up with strategies that humans hadn't thought of in years. But if you read the paper, you'll note that even here, it isn't magic. They used reinforcement learning for policy networks, but then also supervised learning that leverages the human knowledge. So since then, it's really been off and going. Okay, now, when did it start in the environmental sciences and how did it go? So have you had people talk about early environmental science applications yet? How far back do you think it goes? Depends how you consider artificial intelligence or learning from data. When I was a child, my grandfather and father used to say this saying, red at night, sailors delight, red in the morning, sailors take warning. That's prevalent in Western culture. Have you heard that type of saying in Indian culture at all? Some of you are shaking your head. How old is that? Well, the Christian Bible, written about 2,000 years ago, has, he replied, when evening comes, you say it'll be fair weather, for the sky is red, and in the morning, today it'll be stormy, for the sky is red and overcast. Okay, nowadays, we understand some of the rationale for that. Me scattering, preferentially scatters the longer wavelengths, so we start seeing red skies. So it depends whether that weather system is approaching or leaving. We can explain it. But way before we could explain the physics of what happened, people were coming up with observations. So it's at least 2,000 years old. And it's an empirical, based on data, making decisions. We've been doing that for as long as people have been thinking intelligently, really. Okay, so in the environmental sciences, here's the one that we talked before about the boom, winter, boom, winter, boom. And some of the rationale, the Dartmouth Conference in '56, Deep Blue wins at chess, deep learning and go. But at the same time, in the American Meteorological Society is where I was studying the history. The first workshop on AI for Earth Sciences was in 1984. Hosted by NOAA originally. They started having AI shootouts in '89, had another one in '91, and then AMS convened the first real AMS conference in the late '90s, held the first short course in around 2000. That's about the time I started being associated with the committee, had a first AMS contest. I was chair of the committee at that time, and then it became a big deal at National Science Foundation. Some colleagues of mine the project was based at University of Oklahoma. They formed this AI to Earth Sciences project, a big $20 million project with lots of partners across sectors. NOAA was involved, NCAR was involved. Companies like NVIDIA, IBM, et cetera, and had a summer school in 2020. And because it was summer of 2020, everybody was working at home. So the original plan had been to have students come to NCAR for this workshop, but it turned out virtual, and they opened up registration, and we had 5,000 registrants that watched at least parts of this conference. So that was surprising. Okay, so this committee on AI for environmental sciences, a bunch of the past chairs got together to analyze the impact that it's had, and the number of presentations at the AI conferences from '98, this was through 2022, and you see that it started really growing. 2020 was the last big conference that we had the data for. 2021, it was virtual, so of course the numbers and everything went down. 2022, it was planned to be in person, went virtual at the last minute, so there were still a lot, and the last few years have grown even more. So what about the techniques used? How have they evolved in time? Well, neural networks have always been the basis. Okay, for a while we had, then the growth of tree-based methods, random forest, gradient boosting, all those sorts of things, Genetic algorithms, actually a lot of those talks were my students. We were doing a lot of genetic algorithm work in through these years. Fuzzy logic was popular for a while, but kind of died out. Support vector machines, again, less of it now. And what really made a difference is when deep learning came in. And that was in around 2018, right as we're developing and deploying lots of GPUs, and we have the computer capability to finally do that. So think about the timescales. We're talking about millennium for using data to think about how to understand what's going to happen with the weather. Okay, then from the 50s, to about 2015, it started arising, had a bunch of winters, booms and winters. But finally, when our computers start getting big and GPUs, we develop deep learning, and boy, has it taken off, and that's why we're all here today, right? Okay, so when you think back over this, there's two distinct approaches that we have to weather forecasting, and one is the equation-based, okay? So we have the primitive equations, we put a lot of parameterizations in with them, and then we pre-process using data assimilation, post-process, and get solutions. And that's what we've been doing primarily since the 50s. However, there's also that empirically based, everything from the red at night, sailor's delight, to our modern machine learning, where we begin with data, find patterns, and that's where we can make predictions in a different way. And there was a bit of an argument back in in around the 60s, which was going to prevail, the stochastic approach versus the NWP PDE approach. And the PDE approach took over for a while, but I think we're seeing the change come now. So getting to the outline for the rest of my two talks, and we're going to start with the low-hanging fruit. What about post-processing those PDE equations that we've been talking about? That really is something basic. We've been doing it for a while. We're getting better, and it really has improved our forecasts and targeted it to the applications we care about. There's building machine learning parameterizations, replacing some of the slow and some of the unknown parameterizations with machine learning. And then finally, the dynamical core. Can we really build a whole model based on machine learning? And indeed, we've seen lots of examples this week, and I'm sure you've seen some the previous week as well. So we're going to start with this low-hanging fruit, machine learning post-processing. We've all heard about Bob Glahn and some of the simple regression models to post-process, but that's optimizing with multilinear regression. We can actually optimize much more complex ways using machine learning. And NCAR's first big success began back in the 90s. It's building the dynamic integrated forecast system. So the idea is it brings in model output, observations, does a blending, and outputs a forecast. So it's a machine learning post-processor that finds those predictive relationships between model output, the observations, and the desired variables that you want to forecast. It optimizes creating the best combination of inputs. And the idea is it enables decision support because you have real-time data to initialize this, but you also use a large amount of historical data, both in terms of NWP forecasts and the model data. But it works in real time and it uses as much historical data as you want. So originally, it was developed for the Weather Channel in the US, and it was in the 1990s, and they had a group of meteorologists who stared at weather maps and made forecasts for a bunch of US locations. But then they expanded their business to go global and realized they couldn't do this with human meteorologists. So they came to NCAR to create this system that turned out to be die-cast. And it was in the research applications program, which became the lab that I'm now in. And it's used as the weather engine in many projects. So we use it in our surface transportation projects, for solar energy prediction, for wind energy prediction, precision agriculture, and it's been used with a bunch of forecasting companies. Even though it's old technology, in some of the benchmark, they commonly do these benchmark assessments of all the weather forecasting companies, and the die-cast companies are still doing well. The weather company still uses it. They've modified their version quite a lot since then, so has NCAR, for a multitude of other types of clients. So what is die-cast? Okay, so you start with forecasts from a bunch of different models. And in the US, we often care about the global forecast system, NOAA's primary global model, but then they also have a continental US version called the RAP, and then the high resolution rapid refresh, that is the 3-kilometer one. We often in our systems run a customized version of the weather research and forecasting model. The Canadian global environmental model is also free to access. Sometimes we bring in ECMWF if we have a client who's willing to pay for it. And nowadays we're adding machine learning models too. So what die-cast does is it starts by minimizing the error dynamically on each of these models. So that's just, an optimization problem. But then the second and more important part is it constructs weights for each of these models. And the secret to die-cast is it does it dynamically. It does learning every single day for its particular targets. So, of course, it does post-processing and it outputs whatever weather variable you happen to want, whether that just be 2-meter surface temperature, whether it be, wind energy expected at a particular wind farm. So when you look at output error in die-cast, the colored curves here are the input models after they have been bias corrected. So, the RMSE is already down, but then by design, because we train on RMSE, on average, die-cast, the solid black curve, is always going to be less. And in terms of our wind forecasting system, it's typically a 10 to 15% decrease over the best base model. Okay, sure.
This is only for wind forecasting, or this architecture is used for all weather forecasts?
It can be used for all weather forecasting.
Operationally, we're coming.
And that it's not used operationally by NOAA. NOAA is the operational center, and NCAR is a research center. But we do have clients who use it for their private sector forecasts, and it does quite well for everything from temperature, probability of precipitation. There's lots of variables. It has probabilistic prediction built in these days. And, we're always updating it. We're in the midst of, trying to add some of the AI foundation models to it right now, as well as new probabilistic techniques.
So it's like a super ensemble technique you are saying. So you have the hint curves available in the past, and then you reduce the error for individual model. Then you combine it. Like a multi-model super ensemble.
Right. Right. It's like a fancy ensemble, an optimized ensemble, better than just taking an ensemble mean. Okay. And one of the things about die-cast is you can optimize it with as little as 30 days of data. And we typically find that it optimizes best with about 90 days of data to get the most recent seasonality of it. But we drop off a lot of the old data, unlike many other machine learning methods.
Just explain
what kind of optimization you are doing? You are not taking simple ensemble mean, you are doing some optimization.
Yeah, no, it's and it's like it's really something like least squares, a little bit fancier, but very similar to a least squares optimizer on both the bias correction and on the blending part of it.
Okay, so it is far better than taking average.
Uh-huh. Yeah. Yeah, which is why, just kind of blending interesting stochastic techniques, statistical methods, did better than, and I wasn't even at NCAR when they built this, but I was there when we started using it in our renewable energy systems like here. So this is, and I'm not going to talk a lot about variable renewable energy forecasting. First system we built was for Xcel Energy. They were the first company in the US who deployed wind energy at the levels where they were having problems and realizes they needed customized forecasts. So right at the heart of the system is diecast, but we have a lot of data coming in. There's other machine learning methods that I won't take time to talk about in this particular talk, but it has become the centerpiece. Diecast is a centerpiece of many of our forecasting systems. And you'll find that a lot of the NCAR systems have multiple components like this to optimize whatever we're forecasting for. Now, we were working with Xcel Energy, and they wanted to see, they paid us money to build the system. Is it worth it? And when we started the project in 2009, the mean square error was about 17% based on standard NOAA models and that their forecasters were using. By the time the project was finished, we were down to 10% error. So for a percentage improvement of 40%, and they calculated that it saves them $10 million a year on the day-ahead forecast. And that is dollars that are directly passed on to their customers. In addition, they can run the renewable energy more efficiently, which means less coal and gas and oil being used. So they also calculated that for the year 2014, they saved 267,000 tons of CO2. And that was by having a system that included AI/ML. So, that was the point. The AI/ML has not only improved some of the esoteric problems, but it improves things that connect to our day-to-day lives. Now, we were successful with that first project. I wrote a proposal to the Department of Energy to do solar power forecasting. We were awarded a lot of money. We had a big team, included universities, other government labs, private sector companies, et cetera, and built a rather complex forecasting system that we call Sun Forecast. It had both a day-ahead forecasting system, so they can plan how to allocate their units for the following day, as well as a nowcast system. The first 6 hours is critical because if something's going to go wrong, a thunderstorm comes in, all of a sudden there's no solar, they need to be able to fill in. And again, by using machine learning, diecast at the centerpiece of it, other AI methods as well, and we were able to produce this effective system. More recently, we've been working with the country of Kuwait, building their renewable energy forecasting system, CREPS, forecasting for both wind and solar. Again, we have both physical models outlined in dark blue, as well as AI models with diecast right in the middle. You'll see here that at this point, we're starting to emphasize a method called analog ensemble technique. And we heard that terminology before, talk a little bit more about it here in the next slide. So what the analog ensemble does is, instead of building a physical ensemble with lots of NWP runs initialized by stochastic or parameter perturbations, It builds an ensemble based on one, what you hope is a best forecast, hopefully high resolution, where you have the historical forecast and matching data. So you look at the forecast for the lead time you care about. You want to see what the forecast is. Then you look for previous forecasts that were very similar. Now, because they were historical, you know what the verifying observations are. So those verifying observations become your ensemble, and the mean of the ensemble is your deterministic forecast. The PDF becomes your probabilistic forecast. It works quite well. It was originally developed by Luca Della Monica at NCAR. Now, Stefano Alessandrini uses it highly. And you can see here that, for bias, WRF Solar, that was the version of WRF we built specific for solar energy, put out the black curves. The analog ensemble is red, and then a version that had a slight bias correction improved yet more, and you can see the bias is nearly zero. When we apply it to solar power forecasting, in this case, the diecast forecast is in red, verifying obs in black, and the analog ensemble corrects from diecast. But in addition, it provides the probability bars shown here, 25, 75, and then the lighter purple is 5 to 95%. So still improving on the forecast with post-processing with machine learning. So then for Kuwait, we're able to put out forecasts of wind and solar. We combine the probabilities with a technique called the Shikha shuffle, basically reorders. You can't just add probabilities of wind and solar. You have to do something else, and the Shikha shuffle reorders them in a way that you can combine them for an appropriate, reliable PDF of the probability around wind plus solar at their site. And you can see it's, we visited the site, it really is in the Middle East, interesting cases.
Wind forecast which you are giving, are you giving it at the mast level where the turbine is laid, or?
Yes, for wind energy, that's exactly right. We do at hub height. And for renewable energy, we prefer to have observations from the turbines themselves. Now you look at the turbines and you say that can't possibly be representative of the inflow because you have those turning blades. But the important thing is it's representative of the power output. And that's what the utility cares about, is the power output. And I didn't go into details. We also do a machine learning power curve based on data from that particular wind farm that's a lot better than using a manufacturer's power curve, because this one's site specific. It's how it's installed, how it's deployed.
Thank you. Any other question till now? No.
Okay, moving on. So we're going to talk about severe weather AI/ML post-processing. And this is work done by David John Gagné when he was my postdoc back in 2017, published in 2019. And it was one of the first interpretable or explainable papers that came out in the atmospheric sciences. And he used a convolutional network to take radar data. It was actually forecast, it was from a high-resolution WRF simulation that was being run during the severe storm experiment that happens at the National Severe Storm Lab every year that's based at University of Oklahoma. So he took data from that, built a convolutional network where the target is, what is the probability of hail greater than 25 millimeters? So can we predict hail using these machine learning methods? Now, there's a lot of other methods out there, but can he do the convolutional network? And in addition, can he visualize what came out of it? He did this feature visualization by optimization. So once he identifies a storm patch that's probable to produce hail, he puts it through the convolutional net, fixed weights, gets the label, and then the key is he does we forward pass to infer, but then back propagate the error to update the image. What is it that made that particular cell a hail-producing cell? And here's two different case studies. And in both cases, we're looking at 500 millibar, temperature and dew point, 700 H-Pascal and 850. So we're looking at 3 different layers. And we see, on the standard case, this is, what we typically expect. We get, shear, direction and shear at the upper levels, getting this single center vortex. We get confluent moist air at the lower levels, and that's the kind of thing we expect to produce hail. But in addition, he got pictures like this that had a dipole structure, and that actually has been found by Heimsfeld years before, where there is this grapple hail seeder feeder mechanism that was identified. And we were able to see that in these convolutional net cells that were identified, and we could understand why they were producing hail in this case.
Can you explain the contours in the previous, this slide?
Mm-hmm.
What is it that we found? Can you just explain with relation to the contours and the background image?
Right. So and going back one more here, it's this back propagate that we're updating the image to what was really happening. Okay. So we could see what the machine learning saw in these cells that made it predict hail. This is the output of the model, some of the cases that predicted hail.
Background is
Okay, so this is just 2 different cases. One is kind of the standard, supercell upward motion, creating, very strong, creating hail. The other one is a different mechanism, observed by the physical scientists previously, this grapple, feeder mechanism. So, and that was what was surprising about this, that we were able to identify this type of mechanism as being a hail-producing mechanism. And, it verified because we have the data. Okay, so, he did lots of verification scores that I'm not going to talk about. It was more skilled than other models, for hail. But the important thing is it was able to encode the storm features and the hail growth process in ways that we hadn't seen before by using this back propagation step. And then the internal representations can enable more sophisticated analysis for our forecasting models in the future, is what he's showing here. Okay, one more post-processing one, and this is by Will Chapman. He did this when he was a grad student at University of California, San Diego. He visited NCAR during his PhD and then came as a postdoc later. You'll hear his name in the second talk as well. But he was studying atmospheric rivers that hit California. And we want to be able to forecast fields of integrated vapor transport, which is what is going to cause heavy precipitation over California. And with the GFS model, the NCAR's operational model does that. And his question was, can we use machine learning to correct the forecast of GFS What he used as his truth data was the MERA-2 analysis. Somebody else mentioned that. It's NASA's reanalysis. So here we'll see the original forecast from MERA-2 is the what we're what we're seeing as truth, GFS, and then his atmospheric river CNN. Okay, what's really interesting is to look at the difference plots where the atmospheric river CNN minus GFS, it's done a phase shift. Okay, so it's more than just correcting amounts. It's able to phase shift entire patterns. When I saw this work, and you can see this phase shift that makes it better than the original GFS forecast. And there's lots of cases where we know what the incoming weather pattern is going to be. We don't have the timing correct. Where I live in Colorado, when I see a forecast of a thunderstorm, 2 days from now, I always say, no, it's going to be 2.5 days because our NWP models don't have the mountain drag correct. But this is a way to correct it by using things like this. So these are just a few examples of some of the post-processing advances that machine learning is enabling. So what do we need to move forward? Somebody else mentioned the Oxford conference in 2019. I had the honor of leading the downscaling discussion group. We had such a rich discussion. We wrote a paper about it and talked about what do we need to be able to move forward. And again, this was in 2019, so it's a little dated right now. The paper came out a year later. Trustworthiness. We need people to trust it to the point they're going to use it, which involves having it interpretable, explainable. We need the data and the models there that are usable. We need example cases out there. We have to advance our machine learning techniques, and we have been. And we were so passionate about it, about having test cases that people could test their models on, that we archived 5 different test cases on MJO, PNA, GFS, integrated vapor transport, the 2-meter temperature ensemble over Germany, and UK. So these are surface road conditions. These are really disparate type case studies that you can try machine learning. There's also verification codes. So if you pick up these data, you can run it through the verification code. It will automatically compare to a simple regression just to see if you can beat a regression or what anybody else has done. So we also talked about what will constitute success. And that's when we said that it was when the major centers include AI post-processing as a step in how they do their forecasting. And it always bothers me. I go to all the NOAA workshops and they're talking about how to configure their models, and sort of like, you should be evaluating it after post-processing and constructing your ensemble methods in ways that the post-processing will be more successful. I am not aware of that happening in any of the national weather centers yet. Prioritizing computation speed and time for the AI methods, not aware. Well, ECMWF is doing that now, but they may be one of the few, and NOAA's just announcing that they're going that direction. Potential for regime-dependent corrections, like that one, similar we saw, downscaling using AI to save computational power. Maybe we don't need to run models at 3 kilometers. Maybe we can downscale from 25 or whatever. And then machine learning model ensembles. Now, of course, we are seeing some of these latter ones happening now. Okay, any more questions on post-processing? Yes.
So my question is regarding that interpretable deep learning for special severe hail forecasting. So the method that is used for interpretation, that is backward optimization, right?
Right.
So is the task, the project is a regression task or a classification task?
Regression or?
or classification?
It's really a regression task, to
But,
get back. It's doing that back propagation through the net to produce that image. It's not classification.
Actually, I have used that method
You have.
in
Good.
one of my work where I was predicting ISMR, Indian summer monsoon rainfall, using D20 maps, global D20 maps. So that was a regression task, but when I was using backward optimization, it didn't give any insight. It was just random.
Oh, really?
But when I was using that other interpretability method like saliency map and that thing, this was giving a good answer. So I have searched a lot about that, why it was not giving a good interpretability. It was said that it is not usable for regression. So did you faced any problem regarding regression or classification?
Not in this particular case, but I'd love to chat with you more later to hear what you've been doing.
Thank you.
Okay.
Yeah, so this is about the hail and the heavy rain. How good are these things now with the best AI model?
We're getting better at predicting hail. To be honest, hail is not my specialty. So I am not keeping up with the research on that. But I think even David John's work in this particular case, some of the follow-on grad students at University of Oklahoma have been improving it yet further. They had that big project. That's where they do the National Severe Storm Lab, where they are predicting extreme weather in the spring across the middle part of the country. So, I'm not aware of transformative improvements, but I'm sure there are incremental improvements.
So do you envisage any special problems on that for equatorial regions, or?
am not aware of it being applied there. Perhaps, and surely in places like India, people are studying these things. Okay, I'm going to move on to parameterizations. The big example that we've done at NCAR is machine learning for the surface layer parameterization. Okay, now you all learned about NWP in basic physics, and one of the boundary conditions is how do we transfer energy, momentum, and latent heat across the surface? Okay, that's a big question, and it always has been. We typically parameterize it with Mononubikov similarity theory. So that's where you just set up the parameters of importance, and then you have to fit constants, the coefficients that fit data. Now, most of the data that was used to fit were from the prairie grass experiments done in the 1960s in the middle part of the US on flat terrain. So they fit the coefficients there, they put it in our NWP and climate models and use it over the world. Okay, when you think of it, it kind of works, but that's really a source of uncertainty in our NWP models, that we don't really have region specific or area specific. But since it's just fitting coefficients, isn't that ripe for applying machine learning methods if you have data? Now, what we need is tower data where we have temperature, hopefully moisture, and wind at several different levels on a tower to get those fluxes that we care about. We did identify towers that we started using, and these again are kind of flat terrain cases: Kaba in the Netherlands and Schofield, Iowa in northwestern US. And the idea here is we're basing it on the stability functions for momentum heat and latent heat that we're using in this particular part of the project. Now, I'm not going to go through all the details for lack of time. It was pretty much vanilla neural net and random forest. You know what those are, so you don't need those explained. For the Idaho test data, these are two tables that are a little bit complicated. We're looking at friction velocity, the temperature scale that goes into the temperature flux and the moisture scale. And we're comparing on the left R squared, on the right mean absolute error. The top line is MO similarity theory. Okay, this is for the random forest. We have very similar tables for neural net. Trained on the data at that site, in all cases, it beats MO similarity theory. However, what's really interesting is that when we took the model trained at Kaba and applied it to the Idaho site, it still beat MO similarity theory. So we found that machine learning is better. It same happened at the Kaba test case, and the same happened for neural nets. But the conclusion was that the random forest and neural net both significantly outperform standard approaches. And that's true even when applied to a site that's different from the one that it was built for. Okay, that was 2 cases. We did that under a little bit of DOE funding, and it took a few years to get enough funding saying, what about offshore? 3/4 of the globe is covered by water. The ones that we've built for land can't possibly be perfect for water. So can we parameterize the surface layer over the ocean? Now, this is a first, we're in the midst of doing more cases, but the first application was to the Pheno Tower off Germany. It has great flux data and applied, again, both random forest, artificial neural network. And here you see the random forest, the artificial neural network, and MO theory, MAEs for each. And yes, indeed, both methods outperforms Monodukov similarity theory. Okay. The interesting thing about machine learning is you can use it to think about what is important. And you've all seen these importance curves before. Some of the things make sense: potential temperature at 40 meters, mixing ratio at 40 meters, surface temperature, skin temperature. But then we start seeing things like wave height is non-trivial. We use Bulk-Richardson number as a derived variable to get the stability effects. And we see angle between waves and wind, things like that do make an impact on getting it better. And as I said, we're in the midst of doing this for more ocean cases and hoping to generalize it before too long. Okay, I'm gonna grab a drink of water before I get into the downscaling piece. Now, you've heard a lot about the machine learning dynamical core. I'm lumping downscaling there too, because it's the pattern that core actually produces. Now, you've seen that about, I don't know, 6, 7 years, 5, 6 years ago, I saw a talk by one of my NREL colleagues where they were downscaling using a generative adversarial network from climate to mesoscale, from about 100 kilometers down to about 2 kilometers. And at that time, I was leading this project where we were coupling mesoscale models at the order of several kilometers to microscale models at the order of tens of meters. And so we have problems like this that we care about. Let's see if will this start my movie? No. Going to have to go over here to start the movie. But this is a challenge simulation that we did at NCAR. This is my first movie, and it's not playing, unfortunately. Okay, well, the point is that this is a 30-meter simulation over a rather large domain in northwest US in Oregon. Mount Hood is that mountain there. The inflow is from the west. And you end up with very rich features that are observed in the simulation. You get a meandering plume, you get traveling gravity waves, you get stationary gravity waves, cold pools, all kinds of interesting features. So, but this simulation took several weeks on our HPC. using a lot of cores. So, it's something you don't do too often. But can we produce something similar using machine learning if we just had a doable simulation at, say, 1 kilometer? So that was the question we asked. And because we had seen this work of NREL, we decided to try a generative adversarial network. We want to do a downscale from about 1 kilometer. So we coarsened the data to 960 meters. We have this intermediate value at 240. And we did a 32 times downscale. Okay, so full disclosure, doing just 32 time downscale with a GAN was not successful, but we found out that if we could apply a 4 times model first to get to 240, and then an 8 times model to get to 30 meters, we could reproduce the structures amazingly well, even getting the turbulence, really close to the target. So, has somebody talked about the details of a GAN in one of your previous lectures? I haven't seen it this week, but about last week. Okay, I'm just going to give the cartoon version. You can, it's comprised of 2 different parts, the generator and the discriminator. You can think of them as the counterfeiter, who's producing a bunch of data. It's fake, it's cheap. But then the discriminator is the cop that tries to tell whether it's truth data or whether it's made by the generator. So is it LES or is it constructed by the generator? Okay, so you have to, you pit them against each other where you generate a lot of potential simulations. The discriminator tells whether or not it is close to the real. And when you can no longer fool that discriminator, then you have a good generator. Okay, so you could think of it like Turing test for simulations. Now, that means you need 2 different loss functions. For the discriminator loss function, there's 2 different ways that we tried applying it. First, a simple log loss, where you're looking at a function of the real versus the fake. So what is the probability of real versus fake? And you give it the loss appropriately. The second method is the relativistic loss. Again, it's in logarithmic. And the idea here is the sample's realness score depends on classification from the discriminator and the discriminator's ability to correctly sample from those of the class. So in case 1 here, we're on the negative side, so we're pretty far off. So it's going to try to push it closer to the blue. On case 2, it has a good categorization. It's on the positive part of the axis, but it still is not as good as it should. So again, it pushes it from the deduction. On the other hand, we need a generator loss function, and it's pretty typical to do a content loss. Okay, that's just the MAE between the simulated and the real data that you're training to. And then alpha times an adversarial loss, that's based on the discriminator's probability of realness. And then you can add whatever other ones you want. And some of the ones we wanted to say is, something that people use as a perception loss, MAE between the feature maps at the level of the discriminator network, but we also looked at MAE of some physically relevant fields, things like divergence, vorticity, skewness, kurtosis. And we found that especially the divergence was a bit helpful for this problem. Okay, so what do the results look like? Okay, so we start with coarsened data, and we can do super resolution that is able to recover a lot of structure in the data. So that when we look at, compared to the coarsened input data, the original WRF runs on the right that are our targets, and this is independent testing data we're looking at now in terms of, and then the results of our enhanced super resolution GAN in terms of U, V, W. You see we're recovering parts of the turbulence. I was really surprised when I saw that we could, I thought we are never going to get the realization that we'll just get, standard statistics, but we were getting structure, at least at this 30-meter scale, that went beyond what I expected to be able to see. Now, once you build this, you can use the generator to go through a whole domain at once. And you can generate full U versus the original one. Again, amazingly close. And it only takes a second to put out a full domain. But what about, is this generalizable at all? Again, we were working with a challenge simulation. We had done all our training and testing and validation on the eastern portion of the domain. This plots vector ruggedness, and we see that the western part of the domain is much more rugged. That's where Mount Hood actually is, and a lot of its side peaks. Can we use that as a transfer learning and test whether it works in that part of the domain as well? And indeed, we found that it did work, starting with Corsand. This is our result. This is the target that we want to compare to. Very good. Now, we did lots of statistical analyses. My favorite one here is looking at energy spectra. The original LES spectra is blue. We're comparing to the GAN in red. And given the low resolution, big drop off on the low resolution. So the GAN loses in the training region a little bit of energy in the mid-wave numbers, and it shows up as this tail. That's what Ashish was calling the other day a spectral bias that appears in all these things. For our case, it's at places that are dissipated anyway, so we don't really care about it. So we find that it was really quite good. We do the transfer learning region. We lose a little more energy, but it's still quite good. Okay, so this is actually in press right now. I have two copies of the same thing, sorry. So where are we going from here? We're trying it on other models. Let's see if I can get my next movie running. Nope, this one isn't going to have movies that run, sorry. This is a hurricane simulation using Cloud Model 1 developed by George Bryan at NCAR. That was our training data. It does a good job of modeling hurricanes. This particular simulation is at 31 meters. We applied same techniques. The original low res on the left, this is the target. And we are able to generate it rather well. In this case, we've moved to a diffusion model. I'll talk more about our diffusion model in my next lecture. This is the V component. Again, it's working quite well. Summarizing, machine learning is really becoming a necessary component of doing high-level Earth system science these days. And we have in lots of different levels of application, this dynamical core, the model parameterizations, post-processing. We heard some of the other speakers, put things like DA in other categories. Sometimes I add an extra category, where we're learning from the machine learning physics, and there's cases where that happens, kind of like that hail case. But what we're seeing as we're evolving in time is that we're planning this outcome of having better models, understanding the physics better, because we're blending the physics, the observations, and the machine learning. So thank you.
More questions?
Thank you for the lecture, ma'am. So my question is related to the architecture of this. So I understand these are mostly post-processing of the physical models. Was there any physics informed or enforced while post-processing this in the AI architecture?
Okay, so was there physics enforced in which?
The machine learning's architecture? Like, did you introduce any types of physics, or is it just post?
Okay, are you talking about the downscaling problem? I'm sorry, I'm not hearing.
I mean, most of the problems, like you mentioned about
Okay, the
downscaling,
post-processing, no, there was no physics in that at all.
but still it was able to capture very
Yeah.
well detail.
Uh-huh.
Thank you.
So I have a query regarding your downscaling. You have shown some very nice results with your jargon. But that's the low resolution. Did you try with any of the atmospheric data there? Whatever you've shown is a lab setup kind of a situation. So,
You mean use it with real data?
Ah.
No, and that is hard. And okay, so there's actually a lot of caveats here. We trained it with coarsened model data. Okay, we at one point, and the part that did not make the paper or the lecture is we tried to then rerun the model and then apply it directly from the model instead of the coarsened data. And it wasn't nearly as clear. Okay, what we think is happening is that all models have an effective resolution. WRF's effective resolution is about 6 to 8 times the resolution, the grid size. So that when you're doing downscaling from a real model, if it's at 1 kilometer, it's effectively the same as if it were about 6 or 7 kilometers. So the downscale isn't working as effectively, in which case our conclusion, it would be more effective to do the downscale learning from the native model resolution than the coarsened data. In the case of ours, we didn't have the original model simulation and couldn't do that, but for the future, we're going to be trying to do that. In the meantime, we find this to be an interesting discovery. How does that effective model resolution, what does it mean for trying to apply it to real models? And we tried that, we're in the midst of trying it for the hurricane problem. The goal is to run the hurricane at the 1 kilometer. We did it on the IITM1 data, but we ran a hurricane on 1 kilometer, tried downscaling, it wasn't that great, but now we're running it down to 250 meters. Will that be better? What is the effect of this effective resolution? And that's something we can learn about our own models just because we're trying to do this with machine learning.
so another query is regarding your nowcasting that you have shown there in the earlier slides. I noticed that you have used expert systems also. You mentioned there is expert systems.
Mhm.
So that's at what resolution was your nowcasting done?
Okay, so our nowcasting is usually point-based. Okay, so it's at a particular point. Now we do have, and there's a lot of business reasons that we have a version that then grids it and does a nice spreading across the grids, but we can't use it because it's a long story. Our contracts kind of gave it away to a private sector person. So a lot of stupid details. I've been trying to get the funding to build a new fully gridded system. In the meantime, other people have developed those, so it may not be as necessary as it was, when we first realized this was an issue 6, 7 years ago. Yeah.
Ma'am, my question is on the related to the transfer learning that you applied on generative adversarial network. So my question is, have you just fine-tuned only the generator architecture, or you have again used the discriminator adversarial transfer learning?
Okay, it was just take what's trained for the eastern part, apply it over the western part. No new training.
Okay, no new training.
No new training. Yeah, does it work over a different geometry? Nearby geometry in this case.
I mean, same.
We didn't do any fine tuning at all.
Not even fine tuning.
No,
And you got
just
the
applied.
similar result?
Excuse me?
Did you get the similar result?
Yeah, Yeah, we got, we found the downscaling worked extremely well, even though the terrain was very different.
And what is the difference between one location to in terms of the climate and all?
Oh, the climate, they're right next to each other. Climate
Next
is
to
the
each
same.
other.
Yeah, climate is the same. The
Yeah,
big difference, and that's what I'm finding on these downscaling problems. For instance, the hurricane problem was more difficult than because we don't have a bottom forcing condition. For the mountain problem, that terrain forcing sets up boundary conditions that you can imagine a physics model being able to learn modes that could happen in that type of terrain. So it makes sense to me physically why it works when there's terrain. For the hurricane, it would be great if we knew, very fine scale SSTs. We don't. But if you did, maybe it could be better. But we don't have that information. I'll show you in my next lecture applying this over an urban region.
Yeah, I mean, maybe you can test it, but
You have developed the model for a particular region.
Mhm.
Now you tested only the similar kind of the region. Go and can you check it, or you want to check it that where the total different condition, physical conditions are different.
Yeah.
Like there is a dry region like Colorado, other region, and then other one is like East Coast or maybe West Coast or
Yeah.
maybe Seattle area. If you check that, does it work or not?
Great research idea. I agree that's something we should be doing. Unfortunately, we don't have funding to do that. Limited team. That's a bit of the problem, when we're at an organization that we kind of do what our funders have funded us to do. And we have all these great ideas of what to test and we don't have funding. We have to go back on to the next problem.
forward to
Mhm.
this one as your PhD problem or something.
Uh-huh.
Just coming back to the question of downscaling. So you showed that results with that ESR GAN where like from the 960 meter to 30 meter, where you show that you are not expecting to retrieve those turbulent structures, but they appeared. So do you think it's somehow related to the specific architecture of the generator that you chose, that it was able to learn those structures?
Well, and that's what we were trying to explore by doing things like adding vorticity, divergence, the types of things that we think physically would make a difference. We found they made a little bit of a difference, but not as much as we expected. So.
Anyone else?
Mm-hmm. One over here.
I think we shortly discussed this earlier, but is it really practical when we really don't have paired high resolution and small resolution, coarse resolution images for all these things, right?
Okay, that's where we hope that one can do transfer learning on a much larger scale than we demonstrated, just a nearby domain. One hopes that it'll work that way, but we aren't really sure. On the urban problem that I'll talk about later, the vision is that we train over one or two cities, and then we'd be able to apply it over other cities. We don't know if that's true yet.
And regarding that as well, we really should expect some impact of the region, which is like the inhomogeneity in the terrain and stuff like that. So wouldn't it be a good idea to have one model and have another model which is region-based, which corrects, instead of transfer learning, corrects the inhomogeneity in the region and implements it in your...
And that would be a great idea.
A post-processing on the
Yeah.
machine learning now.
Yeah. Now, my colleagues at NREL trained over all of the US on, climate model data, CESM at 1 degree. So about, in the US, that's about 100 kilometers. And we're able to downscale over the entire domain at 2 meters. They used the same, and I didn't go into the details, but a tiling approach where, putting tiles and overlapping tiles, randomizing how you use those tiles. It's a common way to make more data to learn while also not having to hold the whole domain in memory at the same time. And I think because they used that tiling approach, they could do it anywhere in the US, but that was only to 2 kilometers. Now, you obviously can't do 30 meters across the entire US. So if we had more data, then and we're at the place where we're simulating these sorts of things all the time. You can grab data from, repurpose data from other projects, and we're hoping to be able to do that in the future.
So I was really intrigued by the results of the GAN for downscaling.
Yeah.
And where it seems to be learning, and so it's a small follow-up to Adway's question, really, where it seems to be learning structure and statistics. Is there any evidence on what input resolution you need for it to be able to learn the statistics versus the large-scale structure?
Okay, and I think, my assumptions have been that it's similar to physical models where, at 1 kilometer, you're only going to get eddies that fit in a 1 kilometer box. At 30 meters, you're only going to get the size of eddies that fit in a 30-meter box. I'll be showing some simulations that go down to 5 meters, and that's when you're starting to get those very fine scales. But as we saw, when you look at the spectra, it's those very fine scales that are not correct. We got far enough down the spectra that what we cut off didn't make a difference.
Also in those, I'm sorry, I'll discuss with you later.
Yeah.
So we can break for lunch and meet at 2. Okay, thanks again.
Mhm.